Have you ever wondered how the internet actually works? You watch videos, send messages, play online games, and everything just feels instant. But behind the scenes, a constant critical decision is being made about how every single piece of your data should travel across the globe. It's a fundamental choice that shapes your entire online experience, and it all comes down to two main characters, TCP and UDP. Let's dive in. When you send anything over the internet, a photo, a message, a command in a game, it's not sent as one big, single chunk. Instead, it's broken down into thousands of tiny pieces called packets. Think of it like deconstructing a Lego castle into individual bricks to ship it. These packets then travel independently, sometimes taking different paths across the vast network of the internet to reach their destination. A special set of rules, known as a transport protocol, decides exactly how these packets are handled. And the two dominant protocols are TCP and UDP. Let's start with TCP, which stands for Transmission Control Protocol. If TCP had a personality, it would be the reliable, meticulous, slightly obsessive-compulsive one. Its main goal is 100% accuracy. Before sending even a single byte of data, TCP insists on establishing a formal connection. This is done through a process called the three-way handshake. It's like a digital conversation where your computer says, "Hey server, I'd like to send you some data. Are you ready?" The server replies, "Yes, I'm ready. Are you sure you're ready?" And your computer confirms, "Yes, I'm ready. Let's begin." Only after both sides agree that they are ready to communicate does the data transfer start. Once the data starts flowing, TCP's meticulous nature really shines. It assigns a sequence number to every single packet. This is like numbering the pages of a book before you send them. At the destination, TCP uses these numbers to reassemble the packets in the correct order, ensuring the final message is exactly as it was sent. It also performs error checking on each packet to make sure it has not been corrupted during its journey. But here's the most important part. TCP guarantees delivery. It keeps track of every packet it sends. If the receiving end doesn't acknowledge that a specific packet arrived safely, TCP assumes it was lost in transit. It will then automatically resend that missing packet. It'll keep trying until it gets confirmation. This send, check, and resend mechanism makes TCP incredibly reliable. But all this double-checking, handshaking, and resending comes at a cost. Time. This added delay is what we call latency. Because of this, TCP isn't always the fastest option, but it is the safest. That's why it's the go-to protocol for activities where accuracy is non-negotiable. Think about loading a website. If even one packet of the HTML or CSS code is missing or out of order, the entire page could look broken or fail to load. When you download a file, you need every single bit to be perfect. Otherwise, the file will be corrupted and unusable. Sending an email. You definitely want the whole message to arrive, not just parts of it. Software updates are another perfect example. A single missing packet in a software update could crash your entire system. TCP prevents these disasters from happening by prioritizing reliability over raw speed. Now, let's meet its sibling, the wild child of the internet, UDP or User Datagram Protocol. UDP is the complete and total opposite of TCP. If TCP is the meticulous planner, UDP is the spontaneous one who just goes for it. There is no three-way handshake. There is no connection set up. Your computer just starts flinging data packets out into the internet and essentially hopes for the best. UDP doesn't number the packets, so there's no guarantee they'll arrive in order. And most importantly, there is no error correction or resending. If a packet gets lost or corrupted along the way, UDP just shrugs. It doesn't notice, and it certainly doesn't try to send it again. The application on the other end is just left to deal with the missing piece of information. This might sound incredibly risky, and for many things, it is. But this fire-and-forget approach gives UDP one massive undeniable advantage. Speed. By skipping all the handshakes, sequencing, and error checking that slows TCP down, UDP is lightning fast and has incredibly low latency. It's the protocol of choice when you need to get data from point A to point B as quickly as humanly or digitally possible. So, where would you want to use such a seemingly reckless protocol? The answer is, in any real-time application where speed is more important than absolute perfection. The classic example is online gaming. When you're in a fast-paced shooter, you need your character's movements and actions to be reflected on the server instantly. If a single packet representing a tiny positional update gets lost, you don't want the game to freeze and wait for it to be resent. That would make the game unplayable. It's much better for the game to just ignore that lost packet and move on to the next update. You might see a tiny visual glitch or a character momentarily skipping, but the game continues smoothly. Video streaming is another perfect use case. When you're watching a live broadcast or a YouTube video, the stream is a constant flow of data. If one packet representing a single frame out of 30 or 60 per second is lost, you won't even notice. Your brain will just fill in the gap. What you would notice is if the video suddenly froze for a second while TCP tried to re-download that one missing frame. UDP ensures the video keeps playing, prioritizing a smooth, uninterrupted experience over a flawless one. The same logic applies to voice and video calls. On a FaceTime or Zoom call, you want the conversation to feel immediate and real-time. If a packet is lost, you might hear a tiny audio blip or see a momentary pixelation, but the conversation doesn't grind to a halt. UDP makes that real-time feeling possible. Now, here is a crucial point that many people miss. TCP and UDP are not enemies fighting for control of the internet. In fact, they are teammates that work together, often within the very same application. The internet intelligently chooses the right tool for the right job. Let's take a common scenario. You open your browser and go to YouTube. First, your browser uses TCP to load the web page itself, the search bar, the video thumbnails, the comments section. It needs TCP's reliability to make sure the page structure is perfect. But the moment you click play on a video, the system often switches. The video stream itself is frequently delivered using protocols built on top of UDP to ensure playback is smooth and doesn't buffer over tiny network hiccups. Online games do this too. When you first log into your favorite game, you're using TCP. The game needs to reliably verify your username and password and load your character's data. That's a job for TCP. But as soon as you enter the game world and start moving around, the game switches to UDP to send your real-time position and action data as quickly as possible. So, the question isn't which protocol is better. There is no better. The real question is always, which protocol is right for this specific task? It's a constant trade-off. Do you need the guaranteed reliability, ordered delivery, and error correction that TCP provides, even if it means higher latency? Or do you need the raw speed and low latency of UDP, even if it means accepting the risk of losing a few packets along the way? Understanding this fundamental difference really changes how you see the internet. It's not just magic. It's a series of incredibly smart engineering decisions. It explains why your file downloads are always perfect but sometimes slow, why your online games feel so responsive, and why your video streams don't stop and buffer over tiny, insignificant errors. This elegant balance between the careful reliability of TCP and the blazing speed of UDP is what makes the modern internet possible. It's the hidden engine that powers our entire digital world. If you found this deep dive into the internet's inner workings useful and want to learn more about the technology that shapes our lives, make sure to hit that like button and subscribe to the channel. We have a lot more to explore. Thanks for watching, and I'll see you in the next one.